A titration is a procedure used by chemists to determine the concentration of a particular solute in a solution. To understand how titrations work, let's do an example. Let's say we're given an aqueous solution of hydrochloric acid. We don't know the concentration of the solution, but we do know its volume, which is 20 milliliters. To perform a titration, we need a piece of equipment called a burette. Into this burette, we add a 0.100 molar solution of aqueous sodium hydroxide. Since we know the concentration of our sodium hydroxide solution, we call it our known solution. The known solution is also called the titrant. Since we don't know the concentration of our HCl solution, we call it our unknown solution. To do a titration, we're going to add the known solution to the unknown. Before we start doing this, we need to carefully record the initial volume of the solution in our burette. The numerical value of the initial volume doesn't matter. It just matters that we know the exact starting point so that we can compare it to our ending volume later. We also need to add into the hydrochloric acid solution a few drops of phenolphthalein, which is an acid-base indicator. Phenolphthalein is colorless when it's in an acidic environment, but in a basic environment, the indicator will turn the solution pink. Next, we open up the stopcock on the burette and allow the sodium hydroxide to gradually drip into the hydrochloric acid solution. As the sodium hydroxide is added, the aqueous solution of sodium hydroxide reacts with the aqueous solution of hydrochloric acid in an acid-base neutralization reaction to form an aqueous solution of sodium chloride and water. The net ionic equation leaves out all of the ions that don't participate in the reaction. Remember that those ions are called spectator ions. Since sodium ions and chloride ions are present in solution both before and after the acid-base reaction, they are the spectator ions. Therefore, we can take out the spectator ions to give the net ionic equation of OH- plus H plus goes to H2O. So as we add hydroxide ions, we're neutralizing the H plus ions in the unknown. As soon as we've neutralized all of the H plus ions, the unknown solution is no longer acidic. Any additional hydroxide ions will form a basic solution, and the phenolphthalein indicator will turn the solution pink. This color change indicates the endpoint of the titration, and means that all of the acid present in the unknown has been completely neutralized. In the titration, when we see this color change, we should immediately close the stopcock on the burette. At this point, our next step is to record the final volume of the known solution in our burette. We subtract this final volume from the initial volume to find the total volume of base that was needed to neutralize the acid. For this problem, let's say it took 48.6 milliliters of the base to neutralize our acid sample. Given this information, we are now ready to find the concentration of our hydrochloric acid. Since we know that the sodium hydroxide solution was 0.100 molar, and we used 48.6 milliliters of it to neutralize the acid, we can calculate the total number of moles of base that we added. Molarity is equal to moles over the volume of the solution in liters, and so the number of moles equals the molarity times volume. We first convert 48.6 milliliters into 0.0486 liters, and we multiply this number by 0.100 molar to get 0.00486 moles of sodium hydroxide. Since the mole ratio of sodium hydroxide to hydroxide ions is 1:1, 0.00486 is also the number of moles of hydroxide ions in solution. Next, we look at the net ionic equation for the neutralization reaction. Since all of the mole ratios are 1:1, for every mole of hydroxide that we added, we consumed 1 mole of H plus ions and we produced 1 mole of water molecules. So, if we added 0.00486 moles of hydroxide, we must have had 0.00486 moles of H plus ions present in the unknown. The point in a titration where the number of moles of acid is equal to the number of moles of base is called the equivalence point. The goal of a titration is to try to match the equivalence point to the endpoint. Therefore, a titration is stopped the moment the color change occurs. If we continue adding too much base after the equivalence point, we have overshot the titration. To find the concentration of H plus ions, we use the molarity equation. Since we had 0.00486 moles of H plus ions and the original volume was 20.0 milliliters or 0.0200 liters, the concentration is equal to 0.00486 divided by 0.0200, which is 0.243 molar. Since hydrochloric acid is a strong acid, the concentration of H plus ions is equal to the concentration of the HCl solution. Therefore, the starting concentration of the hydrochloric acid solution was 0.243 molar. We could have also done this problem using the MV is equal to MV equation, which states that the molarity of acid times the volume of acid is equal to the molarity of base times the volume of base. Since molarity times volume is equal to moles, this equation is saying that the moles of acid are equal to the moles of base, which would occur at the equivalence point. Since we started with 20.0 milliliters of hydrochloric acid and we used 48.6 milliliters of a 0.100 molar solution of sodium hydroxide, we can solve for the concentration of hydrochloric acid and get 0.243 molar. Note that we can leave the volumes in milliliters and still get the correct answer. Let's do another titration problem. Suppose we use 27.4 milliliters of a 0.154 molar solution of barium hydroxide to completely neutralize a 20.0 milliliter sample of a hydrochloric acid solution. Our goal for this problem is to once again find the starting concentration of hydrochloric acid. Our first step is to write out the balanced equation for what's happening. We have barium hydroxide reacting with hydrochloric acid to form water and barium chloride. Our next step is to figure out how many moles of barium hydroxide were necessary to neutralize our acid. Since molarity is equal to moles over liters, we plug in 0.154 molar is equal to moles divided by 0.0274 liters. 0.154 times 0.0274 gives us 0.00422 moles of barium hydroxide. From the balanced equation, we can see that 1 mole of barium hydroxide neutralizes 2 moles of hydrochloric acid. Therefore, to find out how many moles of hydrochloric acid there are at the equivalence point, we need to multiply the moles of barium hydroxide by 2. 0.00422 times 2 gives us 0.00844 moles of hydrochloric acid. The volume of the HCl solution was 20 milliliters, so to find the concentration of HCl, we take the number of moles, which is 0.00844, and we divide it by the total volume of 20.0 milliliters, or 0.0200 liters. This calculation gives us a final concentration of 0.422 molar for our hydrochloric acid solution. We can also try to solve this problem using the MV is equal to MV equation. Recall that this equation is saying that the moles of acid at the equivalence point is equal to the moles of base. In this equation, we know that the volume of the acid is 20 milliliters and the volume of the base is equal to 27.4 milliliters. We also know that the molarity of the base is 0.154 molar. When we solve for the molarity of the acid, we get 0.211 molar, which is the wrong answer. We didn't get the correct answer because barium hydroxide in this problem is different from sodium hydroxide in the previous problem. When we put sodium hydroxide in solution, it dissociates to form Na+ and OH-. The mole ratio of sodium hydroxide to hydroxide is 1:1. When we put barium hydroxide in solution, we get barium 2+ and 2 OH- ions. So the mole ratio of barium hydroxide to hydroxide is 1:2. So if we have a certain number of moles of barium hydroxide, we get twice as many moles of hydroxide ions in solution. Therefore, to figure out the total number of moles of base, we have to multiply the right side of the equation by 2. Now we get the correct concentration of 0.422 for hydrochloric acid. In addition to using titration to find the concentration of an unknown, we can also use titration to calculate the molar mass of an unknown. Let's say we have a solid sample of a weak acid, and we first find the mass of the solid. Then we dissolve the acid in some distilled water and we measure the final volume of the solution. We can then titrate the solution and calculate the moles of acid that were originally present. Since we know the mass and moles of the weak acid, we can divide the mass by the moles to get grams per mole, which is the molar mass. Since we know the molar mass, we can determine the identity of the unknown acid. Alright, as a quick recap, a titration is a laboratory technique used to determine the concentration of a particular solute in a solution. The first step is to write out the balanced equation for the neutralization reaction. The next step is to determine the moles of the known solution and to use the balanced equation to find the moles of the unknown. The last step is to divide the moles of the unknown solution by the initial volume to get the original concentration. Alternatively, the MV is equal to MV equation can also be used to calculate the original concentration of the unknown.